Alright, so we'd like to evaluate this integral here. This function's a little gross, and we're going to want to apply partial fraction decomposition in order to get this into a simpler form to evaluate the integrals. The focus on this video is going to be demonstrating how to apply concepts of linear algebra and kind of make the process of finding the values of our numerators in our partial fraction decomposition a little more efficient. So looking at this integral, we can see that we have the term x squared here, and that we also have this irreducible quadratic x squared plus 25. Now, because x squared is the same thing as x times x, we know that this whole function is going to be decomposed into the following form. So it's going to be a over x plus b over x squared plus cx plus d over x squared plus 25. And these extensions of the fraction are derived from the definitions and cases involved in partial fraction decomposition. And the next step here is going to be finding the values of a, b, c, and d. So in order to do that, we're going to rewrite the whole fraction here. So it's 7x cubed plus 7x squared plus 125x plus 75. All over x squared times x squared plus 25. And we are saying that this is equivalent to a over x plus b over x squared plus cx plus d over x squared plus 25. And in order to eliminate this denominator, we need to multiply each of these terms such that the denominator is equivalent to x squared times x squared plus 25. So in the case of this first term here, that's going to involve multiplying by x and x squared plus 25 because there's a missing x here for that x squared. For the b, we're going to just be multiplying by the x squared plus 25, and then finally for cx plus d, it's just going to be by x squared. So let's go ahead and rewrite this now that we know that. We're going to say 7x cubed plus 7x squared plus 125x plus 75 equals a times x squared plus 25 plus b times x squared plus 25 plus cx plus d times x squared. And the next step is going to just be distributing all of this. I'm actually going to rewrite this portion right here to make it a little easier to distribute. This is the same thing as a times x cubed plus 25x. Alright, so let's go ahead and rewrite this now, and distributing our actual variables here. We're going to have 7x cubed plus 7x squared plus 125x plus 75 equals ax cubed plus 25ax plus bx squared plus 25b plus cx cubed plus dx squared. Alright. The next step in kind of deriving a, b, c, and d is going to be grouping each one of these reoccurring equivalently degreed variables and factoring out the x cubed or x squared or x. So let's go ahead and do that. So 7x cubed plus 7x squared, so 125x plus 75. It's going to be equal to x cubed times a from right here. And we also have a c, so it's going to be a plus c. Next up would just be x squared, and we have a term here and a term here. So plus x squared times b plus d. And finally, we just have one iteration of x and one iteration of just some number. So this is going to be plus x times 25a and just plus 25b. Okay, so traditionally, this is going to be the part where you would perform back substitution. And given the quantity of terms here, it's actually a couple of operations. And I think it's a nice demonstration of how linear algebra can shorten this process as a whole. So I'm going to start a new page here. I'm going to quickly copy this so that we can pull it up elsewhere. Okay. Alrighty. So the question is now, how do we translate this information into a matrix of some sort? And just as a reminder, a matrix, an augmented matrix, is a collection of all of the coefficients for each variable and we're saying that it's equal to something. And if we look at these expressions, we can say that this 7 right here is equivalent to this a plus c, because both of them are multiplied by x cubed and they both equal something. So from that, we can start to develop these relationships between the coefficients in this expression to the left and our factored expression to the right. So given the fact that we're looking at A, B, C, and D, those are 4 different variables, the amount of columns we're going to have in our matrix is 4, 1 for each variable, plus 1 for the equivalent answer over here. So if we look at x cubed, there would be 1a, 0 b's, 1 c, and 0 d's, and 7 x cubed. And this is the same thing as writing, let's see, ax cubed plus cx cubed equals 7x cubed, right? And we can now go ahead and do this for each of the following terms in our expression on the left. So for x squared, we have b and d. So that's going to be a 0, a 1, a 0, a 1, and another 7. Next up, we just have 25a, which is pretty nice. So just 25, 0, 0, 0, and 125. And then finally 25b, which would just be 0, 25, and 0, 0, and 75. Okay, so now we have a matrix that represents all of the coefficients involved in this system of linear equations and their corresponding values from the left-hand side of the equation. And the question now is, how do I convert this into a simpler form that tells me the value of A, B, C, and D? And the answer is that we're going to utilize the basic operations of matrices for linear algebra. And that consists of multiplying a matrix by some constant, interchanging any 2 rows of a matrix, or replacing a row with the sum of itself plus another row. And what we're going to do here first is I'm going to perform the following operations. So I'm going to do 1 over 25 times row 3, and I'm going to do the same thing to row 4. So 1 over 25 times row 4. And now I'm saying that this matrix is equivalent, and that's what that means here, is equivalent to the following. So 1, 0, 1, 0, 7, 0, 1, 0, 1, 7, and then we have 25 times 1 over 25, which is 1. These zeros wouldn't be affected. And then 125 over 25 is 5. Now we have 0 and 25 times 1 over 25 is going to be 1, 0, 0, and 3. Okay, so this is almost solved. And what we need to do now is we need to reduce this to row echelon form, where we have a pivot in each column, where there is only one number in each one of these columns, and every other number except for that one on this main diagonal here, where I'm hovering over, is a 0. So the operations that I'm going to do to get there is that I'm going to kind of interchange these rows with the sums of other ones. But before I do that, I want to start to kind of organize this so this is a little more visually intuitive. If I was actually computing this personally, just for the problem, I wouldn't do this. But I think for the sake of demonstrating the interactions here, it might be beneficial. So this is the same thing as the following. Right. So now that I've done this, it's actually make it a little easier to manipulate. I'm going to start my next operations here, and I'm going to write them out so that you guys can understand what I'm doing. I'm going to do negative row 1 plus row 2. That's my first operation. So a negative times this row here plus this row here. Negative row 1 plus row 2. The next one I'm going to do is negative row 3 plus row 4. And that's just going to, if we think about it, get rid of these 1s here and here. And it's going to allow us to start really reducing this and start getting closer and closer to a matrix that expresses the value of each one of our variables A, B, C, and D. So let's go ahead and do this. It's going to be 1, 0, 1, 0, 7. And then negative 1 times 1 is negative 1 plus 1 is 0, so 0, 0. Negative 1 times this number right here, this makes this a negative 1. And this is 0. This is negative 7 plus 5 is negative 2. Great. Now let's do it with our next one. And remember, since we're not doing anything to row 3 in actuality, we can actually just rewrite it. Nothing is really happening. But when we think about row 4, we're actually making it the sum of negative 1 times row 3 plus row 4. So it's going to be negative 1 times 1 plus 1, which is 0, and another 0. We're looking at another 0 there. And then 0 times negative 1 is still 0, but there's still 1 here, so this one's going to be a 1. And then negative 1 times 3 is negative 3, plus 7 is 4. All right, so where did this put us? We're at a position that looks pretty scrambled, but if we rearrange some things, it's actually a very, very close solution. There's actually one more operation we need to do, and we're going to do row 2 times negative 1. And that's going to just get rid of these negatives here. And I'm going to just do some reorganizations, but what we found here is an almost solved solution. Let's see here. Great. The only issue here is that we have a 1, and that doesn't follow what we previously defined as a pivot column, where it's just 1, 1 on this diagonal and 0 is all above it. So to get rid of this, we're going to do the following operation. We're going to do row 1 plus negative row 3. So this row right here. That's going to cancel out the 1, because it's going to be negative 1 plus 1. And what that's going to finally get us is our solution, which is 1, 0, 1, 0, 7, 0, 1, 0, 0, 3. Oh, whoops, got that. It's going to be 1, 0, 0, and then we're going to have negative 1 times 2, which is negative 2, plus 7 is 5, and then 0, 1, 0, 0, 3. Oh, whoops. Let me just erase that. Missed a 0. Zero. All right, and this is a completely row-reduced matrix. And now what can we say from this? Well, if we say that this column is A, and so on, down to D, then we can say that 1A, 1 times the variable A, is equal to 5, and so on. So what we get is that A equals 5, B equals 3, C equals 2, and D equals 4. And that's going to allow us to kind of go back to our integral at the very beginning and break it up into the form that we spoke about. So we had 5 over x plus 3 over x squared plus 2x plus d, which is 4, over x squared plus 25. And that is the partial fraction decomposition of the original integrand of our expression.